Before we start to talk about the normal forms, we should talk about normalization in general. Why is normalization important? What exactly is normalization? So in this lesson, we're going to learn a little bit about what normalization is and why we want to do it. Normalization is a war. You are the database designer, and you're going to war against three enemies. These enemies can reduce your data integrity and can make your database less flexible. The first enemy is disarray. If your database has a jumbled organization, it's not going to be very useful to bring information back out. So avoid mixing and matching things willy-nilly. Try to have some really good structure to your database. The second thing you're going to battle against is redundancy. Multiple versions of the truth. Don't store the same information multiple times. That's only leading to trouble. And then the third enemy you are going to face, although this is the least important of all the enemies, are nulls. There's a lot of discussion about nulls and whether they're useful in a database or not, but most people think that minimizing nulls is a good idea, and normalization will take arms against nulls and try to reduce the number of nulls that you have in your database tables. So if disarray or disorganization is the enemy, how do we combat it? And one of the best ways for us to do this is to look at an object-oriented design principle called the single responsibility principle. If you've done object-oriented programming, you'll find a lot of what you learned there carries over to databases. So good database design is good object design. Let's take a quick look and see what we could do. Here you see an employee class, and it has certain attributes: employee number, first name, last name, and then it has department number, department name, and department location. What a jumbled, disorganized mess this is. This is not what you would do. You would not stuff everything into the employee class. Instead, what you would do is you would actually have another department object. And the employee class would have an instance of a department object. And that department object would have the things specific to departments. Everything should have a place. Everything should have one purpose. The employee class should not be describing employee information and the department information. You should have a class for employee and a class for department. And this will carry over to databases, as you will see next. Just look at this table at the bottom of the slide. Its name even gives it away. It's the emp-dept table. So it's already telling you that it's mixing and matching employee information and department information into disarray, into a jumbled organization. So this brings us to our first guideline, guideline number 1 of normalization. Every row of a table should represent one entity or one relationship instance. If we did an ER diagram for employees and departments, they would clearly be two different entities. And therefore, this structure of mixing employees and departments together is not a good one. You should never have attributes of different entities mixed into the same relation, mixed into the same table. What you need to do is to have a foreign key to refer to the other entity. So this employee table should have a foreign key. Maybe that foreign key is department number. The bottom line, when you design a database schema, you should be able to explain it pretty easily. When you have convoluted tables like emp-dept, it's not right. The semantics of the attributes should be very easy to interpret and understand by just looking at your table name and the fields of that table. Our second enemy in normalization is redundancy, or multiple versions of the truth. And we'll use our same emp-dept table, which also falls prey to another three-headed beast. You can only store information one time. If you store information multiple times, you have multiple versions of the truth. For example, let's take a look at these employees. We know that Bob and Jean and Linda all work for the IT department. They all work for Department 45. But how many times do I want to store the information that Department 45 is IT? I stored it once with Bob, I stored it again with Jean, and I stored it one more time with Linda. Not only that, but I'm also storing that the IT department's manager has this social security number. I store that with Bob. I store that again with Jean, and I store it again with Linda. So this three-headed monster is literally represented in our table. I've stored the information 3 times. When you have the same information stored redundantly, this will lead to anomalies, which we will see in the upcoming slides. So why is redundant information really bad? Well, 2 important reasons. The first is that it wastes storage. Why store the same information? For example, the IT department, its name, and its manager's social security number. Why store that over and over again? If I had 100 employees in IT, I'm storing that information 100 times. That's just a waste of storage. But the more important issue is that when you have redundant information, you have problems with data anomalies. And there are 3 kinds of anomalies. There are insertion anomalies, deletion anomalies, and modification anomalies, sometimes called update anomalies. We'll look at each of these in the upcoming slides. Let's look at the update anomaly first. Consider the example that the manager of IT is changing, someone new coming into the role. So I have to obviously update the department manager's social security number. So I can find it here, I can cross it off, and I can put a new number right there. But the problem is, I better do that 3 times because that old department manager's social security number was also in this record, and it was also in this record. And I have to update all 3 records, otherwise I'll have 2 versions of the truth. For example, if Bob's has the new manager of IT and that social security number, but I forget to update Linda, and Linda has the old department manager's social security number, you're left with a question. Who is the real department manager of IT? Because Bob would indicate one person, and Linda's row would indicate another person. This is why you don't want to store information redundantly. Let's consider an insert anomaly, and let's insert a new employee. Let's insert Bert in the bottom row. And so I'll put Bert in the system, and we will get some information about him, and we will put him in Department 42, which, as we all know, is Human Resources. Except it's not, because if you notice up here, with Tina's row, Department 42 had the name HR. And now when I put Bert in, I kind of forgot that it was HR, and I spelled it out, and I made the department name Human Resources. This gives the impression that these are 2 different departments, and it's certainly going to make querying harder to try to find all the departments from HR if you use the department name. So now we have 2 versions of the truth. Department 42. What is it? Is it HR or is it Human Resources? We have a data anomaly. The final anomaly is a delete anomaly. And so let's take the example of Louise. Louise is the only person in our sales department, and she's leaving the company. So of course we want to delete her row from the table. But when we delete her row, we're also deleting the information about Louise. In other words, we're deleting the fact that department number 56 is associated with the name sales. Once we delete the very last employee from that department, the entire department is deleted along with Louise. What we would rather do is we would rather hang on to the department information and just remove Louise from the employee table. This delete anomaly happens because we're mixing information from 2 different entity types into the same table. So this brings us to Guideline 2 of normalization. You should design a database schema that does not suffer from these insertion, deletion, or update anomalies. To do this, you should not have any redundant information in your table rows. Now, there may be cases where some redundancies exist. This could either be because you're dealing with a legacy database that was not designed right the first time, or perhaps your database was denormalized, which we'll talk about in some upcoming lessons. It is not best practice to have data redundancies. If they are there, however, the only way you can deal with those is to make applications to update and to insert and to delete. So for example, when we were updating the IT manager, we did it at one row. We did an update statement for one row, for Bob's row. Instead, there should be a database procedure that's used that will make sure that every single row where IT is listed, the manager is updated in all three rows. In other words, the application itself will have to take control of the data integrity. But again, it is important that you do not design for redundant information in table rows. That is Guideline 2. Finally, on to Guideline 3. Guideline 3 of normalization says that your relations, your tables, should be designed so that their rows have as few null values as possible. So this war on null is for a particularly good reason. And the reason is that nulls don't have much meaning. It's just the absence of information. So what does a null mean? What could a null mean? A null could mean that the attribute is not applicable. Say, for example, your middle initial if you don't have a middle name. But a null could also mean that the attribute value is unknown. Maybe my middle initial isn't known to someone putting my name into the database, but it might really exist. Or maybe the value is known to exist, but it's unavailable. You can't look it up, you have no records for it. So all you know if a field is null is that there's no information. So Guideline 3 says to minimize nulls. Of all the guidelines, Guideline 3 is the one that you might violate more often than not. It is the weakest of the guidelines. But we will explain why nulls are not good in the next slide. Once again, here's our table of employees. We've added a new column. We've added a column to keep track of the highest security certification employees have received. But not every employee is going to get a security certification. We know that Bob has the Security Plus certification. We can see that Linda has the CISSP certification. But when we look at Jean, we realize that Jean has a null value there. What does it mean? Does it mean that Jean did not get a security certification? Or does it mean that he maybe got one, but we're not sure which one he got? These are why we don't like to have nulls, because they're difficult to interpret. So instead of having a column reserved for the security certification and having all those null values, instead what we could do is we could put it in its own table. And here's a table called the Security Certification Table. It lists the social security numbers of the employees along with their highest security certification. In this way, there are no nulls. There are no unknowns about Tina and Louise. They simply do not exist in a security certification table. And we're also not wasting space by reserving database space for fields that have no value. So in conclusion, these are the benefits of normalization. You will have less data inconsistency by not having the data anomalies. Data redundancy is minimized. That simplifies your maintenance and reduces your storage requirements. You'll have clearer data relationships as every table has its own purpose and it does not mix information from multiple entities. You'll have a flexible data structure, which means that as your application grows, you can easily add more tables and relations. You will have more tables when you normalize, and every table will have an index on its primary key. That's going to make data retrieval more efficient. Again, every table has information about a single entity, making retrieval and insert and update and delete operations more efficient. And finally, every table is going to have fewer indexes. Indexes take its toll when you do inserts, updates, and deletes, and therefore these operations become more efficient. So for all these reasons, we do want to normalize. We'll find out how in upcoming lectures.